Okay, welcome back here. Start here in just a second. Kind of continue on going through. Okay, so let us kind of continue on here. So we talked about sort of stoichiometry. We talked about percent yield. And again, we use percent yield. Again, the higher the percent yield, the better the sort of reaction was done. The smaller value, obviously some error was put into there. Then we kind of talked about titrations. And titrations really is stoichiometry, is sort of solution stoichiometry. But before we got into that, we did talk about some concentration units of solutions. Remember that solutions are basically two things. It's a solute, which is the smaller part that's dissolved in there, and it is the solvent, which is the larger part that's you dissolve it in. So again, a sodium chloride solution, and a solution typically will have that aqueous symbol next to it. The sodium chloride would be the solute, the solvent would be the water in that particular case. Now, we talk about sort of concentrations involving these guys, and we saw a couple of different types of concentrations. We saw percent mass to mass, which is the mass of the solute divided by the mass of the solution times 100%. There are also percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. And there was percent volume to volume, which was the volume of solute divided by the volume of solution times 100%. And remember that, these we can use, if we had a 4.5% mass to mass sodium chloride solution, we could turn those into sort of usable conversion factors. That would be 4.5 grams of sodium chloride and 100 grams of solution, or you could reverse it the opposite way, 100 grams of solution and 4.5 grams of sodium chloride. So that's a way you can kind of take the percentages and use them as sort of useful conversion factors. Remember that this one here is the one that gives people problems sometimes. It is the mass of the solution, so you want to make sure that you do get both the solute and the solvent together. And that's a big problem in these type of problems because typically speaking, they will give you the mass of the solute and the mass of the solvent kind of separate from each other. So it's important to make sure that you do add them together. We also then sort of talked about really the main sort of unit of concentration for solutions, which is molarity, and that is moles of solute over liters of solution. And basically molarity can be thought of as a conversion, right? Factor, moles per liter. We could rearrange this and solve for liters. It would be moles divided by the molarity. And also moles would equal liters times the molarity as well. So those are three sort of versions of it. In solution stoichiometry, a lot of times we use that version there to get to moles. So that's a very common sort of conversion that you need to do. We also talked about dilution. Dilution is when you take something that has a higher concentration and most of the time add more solvent, so more water molecules, and it lowers the concentration. And there is a dilution equation, which most people use as M1V1 equals M2V2. Again, here, sometimes people will just use more of a generic term, like C1V1 equals C2V2. C just means concentration. So as we talked about, although a majority of the time it is molarity that you're probably going to be using there, Since it is the most kind of common unit of concentration, it doesn't necessarily have to be molarity there. You could, for example, use any of those percent concentrations we just saw in that sort of formula here. Remember that though, when we use this, typically speaking, this is before the dilution. So that's usually your more concentrated. And this is after usually, and that is your less concentrated. And the important part is that the moles of the solute before the dilution equals the moles of the solute after the dilution. Again, the only thing that we're adding is more solvent, and in a lot of cases that solvent is water, so we're just adding more water in there. And really the thing that it affects is this part of it. So by adding more water or solvent, we're just increasing this bottom number, and the result of that is the molarity comes down in terms of its overall value or number. We also, I think, sort of in this area talked about a couple other sort of units that we saw in a couple of different places. We talked about the idea of mole fraction. And the mole fraction is that X value where you take the moles of what you're interested in divided by the total moles. And again, here we don't multiply by 100, so it's not a percentage, so it's just like a point number. We also saw molality, I think, around this time as well for the first time, and the molality is the small m, and that is moles of solute over a kilogram of solvent. And so sometimes just moles per kilogram is sort of the unit. So we also kind of got into really solution stoichiometry, which is really titrations. Doesn't necessarily have to be, but titration, solution stoichiometry. And when we do titrations, as we talked about, we basically use a burette, like we had that big lab on. And, you know, you have a flask or a beaker or something down here. And for example, in an acid-base titration, for example, you can put your sodium hydroxide up here. You can put your acid down here. You also would put an indicator in there. The indicator changes color. And the indicator will change color around where the equivalence point is in a titration. And in an acid-base titration, that is when the moles of acid equals the moles of base. That's the point where you've exactly sort of neutralized all of the acid that was there with, say, the base that you're adding. Definition of a titration is when you add really a solution of known molarity to a solution of unknown molarity. So you really have one unknown. And really what titration problems are really just stoichiometry problems. And they're really work the same way as stoichiometry problems, which means you still need that sort of the basic steps. You need that balanced equation. You need to convert to moles. And really in a stoichiometry problem where it sort of deviates from a normal one, our titration problem here is the way that we get our moles. And typically the way we get our moles is we use liters times our molarity. And that gives us our moles. So usually in a titration problem, you have some volume given to you, maybe in milliliters, you need to convert to liters. You usually have the molarity given to you, and you again can use that to do that. The rest of it is kind of the same. You do the mole to mole relationship. And the other difference is number 4 here, where we go from moles to some other unit. Also on the back end here, we oftentimes will use molarity in the calculation. So for example, we may take the moles that we got and then divide it by the volume to actually calculate the molarity. We may use the moles that we had and the molarity given to us and divide by it. to get the volume of something. So those are very common things that you're asked for in sort of titration problems or solution stoichiometry problems. What is the molarity of something at the end? What is the volume of something? And again, the kind of middle part of the calculation is really the same. It's really just your basic stoichiometry problem that's being done. Also, obviously need a balanced equation. So if you had something like H2SO4 plus some sodium hydroxide, gets you some Na2SO4 plus some water. And maybe like a 2 there, 2 there, and that looks good for our 2s, I think. So again, you want to make sure you always balance the equation. So if it said, hey, you started with 10 milliliters of 0.1 molars sodium hydroxide, and it took, 20 milliliters of this guy to get there, you would start the problem like we did. You'd have the balanced equation. You want to convert that volume into liters. You want to use the molarity here of your sodium hydroxide. That will give you your moles of sodium hydroxide. You then could use the balanced equation, 2 moles of sodium hydroxide, 1 mole of H2SO4 will give you the moles of H2SO4. And once you have the moles of H2SO4, you have the volume. So in this particular case, we could divide it by the volume converted to liters, and that will get you to your molarity. And again, that's a very common sort of question that's sort of tried to figure out in a titration problem. So solution stoichiometry could also be, you start with grams and you convert the grams to moles. You do the mole to mole relationship, and then again, using the molarity at the end, figure out the volume of something that you produce. So again, there's some variations on this problem, but the basic steps are still a stoichiometry problem, as we talked about a number of times. Also remember that you potentially could have 2 solutions mixed together, which means you have the volume and the molarity of both solutions, which means that you technically would have, again, a limiting reagent problem, happening as well. So you can have, again, a limiting reagent problem involving solutions, just like we talked about. You could have it like perhaps involving gases as well. So remember, just to keep that in the back of your mind, don't just think that limiting reagents is maybe just grams and moles and stuff like that. It can happen in a couple different places. But the basic steps here, again, are still basically the same steps as what we sort of saw before. All right, so I think at that point we sort of rolled into some gases, I think. So we started talking about some gas laws, obviously. We had a bunch of gas laws. Gases involve, obviously, pressure and some common units. Atmosphere, 760 torr equals 760 millimeters of mercury. Remember, that is sort of our conversion factor to go from atmospheres to torr or millimeters of mercury. And that's because millimeters of mercury is the same as a torr. It's a 1-to-1 relationship between those two. Not the only units that we see in terms of pressure. There's bar, there's pascals, kilopascals are common ones. So we looked at a number of gas laws that involved sort of relationships, and we had our Boyle's law, which was our P1 V1 equals P2 V2, and this was at constant, what we got there, temperature. In terms of the pressures, it doesn't matter the units as long as they're the same. The volume, same deal, doesn't matter as long as they're the same. We also saw Charles' law. And in Charles' law, we had like V1 T1 equals V2 T2. This would be at constant pressure. Volume doesn't matter to units, but the temperature, like every gas sort of law, does need to be in Kelvin. By the way, in terms of Boyle, we saw the relationship is as the pressure goes up, the volume goes down, and vice versa. Here, as the volume goes up, so does the temperature. And as the volume goes down, so does the temperature as well. Obviously, this one is opposite. We also saw Guy-Lussac's law, which is P1T1 equals P2T2. This is at constant volume. So in this particular case, at constant volume, because the volume will not adjust to the change in pressure, we actually do see a rise in pressure, Kelvin as well here for our temperature. Pressure could be any units you want as long as they are the same. So in this particular case, as the temperature increases, so does the pressure. And that's again because the volume's not moving. And as the temperature goes down, so does the pressure there. We also saw, excuse me, some other relationships. We saw Avogadro's law. That was V1N1 equals V2N2. This is at constant volume, not volume, sorry, constant pressure and temperature. N is the moles of gas. V is volume. So again, you could use this as we talked about sort of just like it is and plug and chug the numbers into there. We also saw that sort of a consequence of this relationship was you could actually use this in sort of stoichiometry problems. So if you had 2A plus 3B goes to 4C, and they're all gases at constant pressure and temperature, instead of a mole to mole relationship there, you could do a like volume to volume relationship and say 2 liters of A equals 3 liters of B. 2 liters of A gives us 4 liters of C. So sort of a practical application there of Avogadro's law is that you can sort of do a mole to mole relationship without having to necessarily use the ideal gas law or anything like that to sort of solve this stoichiometry problem. Now, speaking of that, if we kind of put everybody together there, we do get that ideal gas law. And that is our PV equals nRT. And remember that the ideal gas law, unlike the other ones, there are for sort of a one case situation. And here, though it is the most restrictive, pressure has to be in atmospheres, volume has to be in liters, N is in moles, R is our gas constant, 0.08206 liters atmosphere Kelvin mole. Our T is our temperature, which needs to be in Kelvin as well. And this is all those units because of the gas constant, because of the units that we see associated with the gas constant. And we also talked about the idea of STP, which is standard temp and pressure. And when we say STP, that means the temperature is 273 Kelvin, pressure is 1 atmosphere. And basically, there is a nice little conversion factor that allows you perhaps not to have to use the ideal gas law, is when you are at STP and only at STP, 1 mole of any gas will equal 22.414 liters. So again, a reminder that this conversion here is only for a specific sort of set of conditions, which is our standard temperature and pressure. So if you're not at standard temperature and pressure, then you cannot use that. You do have to use the ideal gas law. You can use the ideal gas law in any situation. Standard temperature and pressure are normal conditions or other outside of that, or you could use, but you can only use that conversion for standard temperature and pressure. We also saw that we had the combined gas law. And that was our P1 V1 over T1 equals P2 V2 over T2. Here, again, Kelvin for our temperatures. Pressures and volumes doesn't really matter. They could be the same units, and you're okay to use that. Same thing again with our volume there. So let's see. In terms of ideal gas as well, by the way, as we talked about, right, there's really two things that sort of make something an ideal gas, and under most times, most gases will behave pretty ideally under normal pressures and temperatures. And the two things that really make something an ideal gas is we assume that the volume of the gas itself is 0 compared to the volume of the container it's in. So we really look at sort of the volume of the container rather than the gas itself, because it's sort of negligible, the volume of the gas itself compared to the big containers flying around in. Secondly, what makes something sort of an ideal gas is the idea that there is really no interaction between one gas molecule and another. And that is because if in an ideal situation, that allows us to treat each gas sort of separately, even if we have sort of a mixture of gases together. In that sort of ideal situation, one gas molecule will not have any effect on the other gas molecule as they are flying around. We then also talked about ways to solve for a couple of things like density of a gas and also the molar mass of a gas. And the density of a gas is the pressure RT times the molar mass. And as we talked about, really all these come from the ideal gas law. So we took PV equals nRT, and you solve for N over V. It would be P over RT. That gives you moles per liter. And you could use the molar mass from the periodic table, and that gives you grams per liter, which is the typical units of density for a gas as well. For the molar mass, we could do the density times RT over P for the molar mass. And again, that's sort of a shortcut way that you could do it, but this also is from the ideal gas law, and really molar mass is grams per mole. So in most of those type of problems, you're given the grams, and you really could use PV equals nRT and solve for N, which would give us PV over RT, and then you would have the moles part as well. So we talked about, again, how to sort of calculate those things. Using the ideal gas law, again, you could use sort of the shortcut formula for it as well. We also talked about gas stoichiometry, and gas stoichiometry, like all the other sort of stoichiometry we've been talking about this semester. Again, your same basic 4 steps. Your balance your equation, your convert to moles. And in a lot of cases, you are going to do grams to moles using the molar mass. Potentially, you could also use the ideal gas law here and solve for N if it is that type of problem. You're going to do your mole to mole relationship, and then you're going to convert those moles usually into liters. And that usually will involve using PV equals nRT at the end of the problem, where you solve for V, which would be here. So in a lot of sort of gas stoichiometry problems, you know, you have grams of something that's not a gas, so you need to convert it into moles. Do the mole to mole relationship between that substance and the gas, and then use the gas information like temperature, pressure, etc., to figure out the actual volume of that gas that would be produced. And again, that's a very common sort of gas stoichiometry problem that is used. Now, in terms of gases, we also talked about mixtures of gases. So when we have a mixture of gases, when we have multiple gases in one container, the nice thing is the volume is going to be the same and the temperature is going to be the same for all of the gases that are flying around in there. And because we assume really an ideal situation, even though there's multiple gases kind of flying around, we assume that, again, there's going to be really no interaction between them. And we wouldn't expect them to have one effect on the other. So even though there's multiple gases in a container, we can basically treat them as almost if they are there by themselves. So we can solve for the total pressure, which is the partial pressures of however many gases you got in there. So that's what each of these P's represent, the partial pressures, because when you add them together, you get the total pressure. And the most common way to do that is to take the ideal gas law and basically solve for P for each of the gases individually. And then obviously you could add them up to get the total pressure in that mixture. Now, if you don't have enough information perhaps to use the ideal gas law, this is again a place where we saw our mole fraction that we could use. And that formula where we have P of A is equal to X of A times PT. And this is our partial pressure of a gas. This is our total pressure. And this again is our mole fraction like we talked about. And you could use this sort of equation here if you're given perhaps, say, just the grams of the gases that are there. Maybe the moles of the gases as well. And you have like the total pressure given to you, or maybe one of the partial pressures. Again, this is a way that you could kind of solve it if you don't have things like temperature or other factors involved in that problem. Another sort of partial pressure situation that occurs is when we collect a gas over water. And when you do that, it gets what is sometimes referred to as being saturated with water vapor. So basically what that means is, in addition to the gas you're interested in collecting, you're also collecting water vapor in there as well, which has an effect on the pressure. So you usually have to do sort of a correction for that, where you take the total pressure is the pressure of the gas you're interested in plus the vapor pressure of water, which is this guy. And the vapor pressure of water is essentially a value you can look up based on temperature. And if you rearrange this, this will give you the pressure of your gas is the total pressure minus the pressure of water in that case. So we had a couple of experiments where you had to kind of correct, or at least one experiment where you had to correct for that and figure out, again, sort of the dry water pressure that was involved in there for that gas. In addition, we also talked about sort of the speed at which gas molecules travel, and that is what is sometimes referred to as the root mean square velocity, which is the square root of 3RT over the molar mass. And what we saw was that if you take the same gas molecule and you increase the temperature, the speed at which it travels will increase. So it'll start to travel at a much higher speed. If you look at three sort of different gas molecules or different gas molecules, the speed at which they travel is affected by the actual molar mass of those guys. So the heavier the gas molecule, the slower it's going to be moving. The lighter the gas molecule, the faster it's going to be whizzing by and be able to move just based on its molar mass. So those are sort of the two comparisons we talked about when we talked about sort of the speed of a gas. And a couple of things about this equation here. R is actually the gas constant that involves energy. It's the 8.314 version of it. And again, here where we see that joule is a kilogram meter squared second squared. And the purpose of this is that's essentially how we're going to get to the units that we need. And that means that instead of grams per mole here, when we use this equation, we do need kilograms per mole so that everything cancels out. And again, in terms of the units, what you'll end up with is kilograms. Where are we at here? Kilograms meter squared second squared And then you also have your Kelvin and your mole. And you're going to times that by Kelvin, which is the temperature. And then if we take our kilograms per mole and do a whole bunch of canceling, kilograms cancel, kelvins cancel, moles cancel. When we take the square root of our meter squared over second squared, we end up with a velocity in the units of meters per second. The good news is, again, even though it is technically joules is a kilogram meter squared second squared, it's a one-to-one relationship, which means the value of R is the same regardless if you use joules or if you separate out the units. So really the only important thing here that you have to make sure that you change is the units for the molar mass. You definitely need to get those guys into kilogram so that everything basically cancels out correctly. We also talked about gas diffusion, which is sort of the gradual mixing. And again, the rate or speed of gases affect that. Again, if you have that slower moving gas molecule, the faster moving gas molecule is going to get over there. So I think we saw maybe a picture of HCl and ammonia, and the ammonium chloride that's being made by that happens closer to the slower moving gas than the faster moving gas in that case. And there is sort of a formula that goes with gas diffusion. Which is rate 1 over rate 2 equals the square root of M2 over M1. So I think we might even did an example where we figured out sort of a formula based on not gas diffusion, but we actually looked at, I think it was gas effusion. And gas effusion is sort of that mixing process by which gas molecule kind of escapes through a hole, basically in a container from one side to the next. And sort of the similar formula as we just saw there, rates in T's or times equals our square root of the molar mass of one and the molar mass of another. Again, these are molar mass in this instant here. So these are a couple of things we talked about there towards the end of the chapter there on gases. And then what we really talked about, right, was the idea of not an ideal gas, but what is referred to as a real gas. And a real gas occurs at really high pressures and low temperatures. So when we get to these situations at really high temperatures, low temperatures and high pressures, we get to a situation where at high pressures, that means the volume's got to be pretty small. And at really high pressures, the volume is really small, which means just by that process, those gas molecules, again, are really close to each other, which means they're going to have to interact with each other. And in addition, if we also have low temperature, they're going to be moving slower, which means they're going to be in contact with each other for a much longer period of time than if it was kind of moving around really fast. They're not really in contact with each other for a very long time. So when we get to those situations of really high pressures and low temperatures, again, that makes all these gas molecules really be near each other for a very long period of time. And there's going to be interactions. And if you remember, that ideal gas is something where we assume that there is no interaction between gas molecules. So under these conditions, it's sort of forced upon them to have to interact with each other. And in addition, because of those high pressures, for example, the volume of the container has got to be relatively small. So now the volume of the actual gas molecule itself is going to be relatively important as well. And our good friend van der Waals basically came up with some of those relationships there. And really what he did was he basically put some correction factors into the ideal gas law and made what is sometimes referred to as the van der Waals equation for non-ideal gases. And it looks something like, what we got here, P plus AN squared over V squared And that is that part of it, which looks like the ideal gas law. That's sort of the correction factor for the pressure. So this corrects the pressure. And the A here is van der Waals constant value, and that is a value, again, that you can look up in a table, and it's different for each gas. And V minus NB, B here again going to be another van der Waals constant, also different for another gas. And this corrects sort of the volume relationship that occurs in these conditions. And this equals our nRT. And this is what is sometimes referred to as the van der Waals equation. Everybody else in this equation is the same as in the ideal gas law, which means, again, pressure needs to be in atmospheres, temperature, Kelvin, volume in liters. And again, you look those up. And it really is sort of the ideal gas law with some correction values for that in these non-ideal situations. And as we talked about, you know, we use the ideal gas law because really under normal conditions, there isn't a lot of deviation from an ideal situation. You really have to get into some pretty good size pressures to really start to see some really noticeable some deviations from ideal behavior. And that's why we usually just use a lot of cases and consider most things to behave ideally. And we use our ideal gas law to do that, again, because it's more universal, if you will. This one here, the van der Waals equation, again, you have to look up A and B values for different gases. So, you know, it's a little bit more of a specific equation for those conditions. But again, it sort of corrects the situation that occurs when we have sort of that non-ideal situation. Let's see, I think that wraps pretty much gases. Then we rolled on to the idea of, speaking of van der Waals, some intermolecular forces, intramolecular forces. So if you remember, there's really two types of forces that holds everybody together. There's intramolecular forces and intermolecular forces. The difference here is intramolecular force is the force that holds one sort of molecule together. So for example, as we talked about, if you took just one individual water molecule, it is really that covalent bond between the hydrogen and the oxygen on both sides that holds that together. That would be intramolecular force within the molecule. So covalent bonding, ionic bonding is also intramolecular force. And that's different than intermolecular force. That is the force that holds two molecules together. And that would be like an example if we took a couple of water molecules, again being polar, oxygen more negative, hydrogen more positive, positive, negative. And again, all of the intermolecular forces are really this sort of interaction, that electrostatic interaction, that positive negative interaction that holds those things together. As we talked about, intramolecular forces always 100% more strong than intermolecular forces. So as we talked about, if it was opposite, everybody would fall apart here. We would have hydrogen gas, oxygen gas being made when we boil water, for example. But when we boil water, for example, the first bond that breaks is the bond, as we talked about, between the two water molecules. And that's why we get water to go from obviously liquid to gas, and we get the whole the water molecule in the gas phase, and not hydrogen gas or oxygen gas. And it's responsible for intermolecular forces, things like boiling points, melting points. The stronger the intermolecular force, the higher the boiling points, melting points would be. The sort of weaker the intermolecular force, the weaker or the lower those things like boiling points would be. So we talked about some specific types of intermolecular forces. There's really sort of three big categories of them. And the first one really is dipole-dipole interaction. And dipole-dipole interaction is when we have really polar molecules and polar molecules coming together, either a polar molecule with itself or a polar molecule with another polar molecule. And basically, because they are polar, they have a fixed side that's positive in the molecule and a fixed side that's negative in the molecule. And when they get together with another polar molecule that also has a fixed positive and negative side, they have a place where they can interact with each other. And again, that's your dipole-dipole interaction. A special type of dipole-dipole interaction that we talked about is hydrogen bonding. And it really is sort of a special type of dipole-dipole. And it involves a bond between hydrogen and nitrogen, oxygen, and fluorine. And again, if you look at the periodic table, that is your three kind of most electronegativity type values are heading that way. Fluorine obviously being the most electronegativity or electronegative, I get that word right. And because of that strong electronegativity that's found there, when it hooks up with hydrogen, you get a pretty good separation of charge. So if you remember just off the top of my head, we did that HF type of deal. The change in electronegativity was 1.9, right? 1.9 is a pretty big difference in electronegativity. If you think about 2 is usually the cutoff for the electrons actually being transferred. And because of that, you get such a big separation of charge, you get this really stronger bond that forms when hydrogen is involved in that. And that is actually the bond that is what we just saw on the previous slide and talked about many times, what happens in water. Water, again, being polar, has a negative and a positive. And again, it's that opposite bonding here. Hydrogen here attached to an oxygen, able to participate in hydrogen bond. Remember, as we talked about, just because you see hydrogens does not mean it could hydrogen bond. This guy here has a ton of hydrogens, but the carbon-hydrogen bond is nonpolar, which means this hydrogen is not attached to oxygen, nitrogen, or fluorine, which means this guy cannot hydrogen bond, even though he has a lot of hydrogens there. What that guy can do, though, is he uses what is referred to usually as dispersion forces. And these dispersion forces are these relatively weak interactions that occur in normally nonpolar molecules. So if you have a nonpolar molecule and a nonpolar molecule, the electrons which are moving around all could kind of move over, as we talked about, to one side versus the other. And what that will happen is in this normally neutral guy, nonpolar guy, he temporarily gets a charge. And because the electrons are here, it's going to cause the electrons in this guy to head the other way. And now this other guy that normally doesn't have a charge will temporarily gain a charge. And now these two guys, again, temporarily have a way to interact with each other. The ability of those electrons to sort of shift is what's known as polarizability, and it increases with molar mass. So the more molar mass you have, that means the more elements you have, more elements you have, more atoms you have, more atoms you have, more electrons you have. So there's a greater chance of that happening, and also increases the strength of dispersion forces. So something that is bigger in molar mass typically will be a stronger bond in terms of dispersion forces than something that is less in molar mass in that case. These are weak because they will temporarily break apart and form new ones, temporarily break apart and form new ones. You could also induce this by putting a dipole next to it, a polar molecule or an ion next to it. We talked about dipole-induced dipole and ion-induced dipole. And this is sort of, if you just want to think about sort of what happens, you know, when you mix something, that's polar and non-polar, like oil and vinegar or something like that. You know, for a little bit, they're able to kind of hang in there, and then after a while, they sort of separate out, because over the long period of time, they don't really have a way to maintain those connections like they do in hydrogen bonding and dipole. And again, the difference between those is when you have a polar molecule, what that means is it has a fixed positive side and negative side because it has a dipole moment, like we talked about in bonding. And what that means is no matter what the situation is, if it's a polar molecule, it's good to go. It's got a positive side and negative side. So it's perfectly good to really start binding and doing these intermolecular forces. Now, when you have something that is nonpolar, it's not able to do that because it's got to rely upon either the electrons moving around to create this temporary charge in it, or it's got to have something come near it to also create a temporary charge. So in terms of strength, out of all three of these, your hydrogen bonding is your strongest, followed by your dipole, and your weakest out of all three of these is your dispersion forces. So mainly, hydrogen bonding is used for polar molecules that have the ability to hydrogen bond. Dipole is used for polar molecules that do not have the ability to hydrogen bond. So something like PF3, for example, it's trigonal planar, doesn't have hydrogens, but still polar, able to dipole interaction. And really, dispersion forces are used for guys that are non-polar and non-polar in terms of their interaction. We then also talked a little bit about the idea of sort of water and some properties of solution. We talked about, you know, cohesive and adhesive forces in terms of, you know, affecting things. So when we look at, you know, for example, cohesive, adhesive forces, you know, we talked about the idea that, you know, that's sort of what creates that meniscus that we see in a container, you know, say water in a glass container, say mercury in a glass container versus water. And the reason this is curving like that, as we talked about, is part of the situation here is the attractive forces between, say, water and the glass tube is stronger than the attractive forces between water and itself. So what ends up happening is we get the solution sort of rising through sort of capillary action up the tube there. And that's different than, say, something like mercury here, where the attractive forces between mercury and itself is stronger than mercury in the glass tube. And we get this sort of reverse meniscus that sort of occurs. We also talked about the idea of vapor pressure. And remember, vapor pressure and sort of the idea of liquid in a container versus out of a container. You know, if you just had a liquid out on the bench, the process at the surface of the liquid, right, there's always that process of evaporation and condensation happening. So you got a lot of rate of evaporation happening all over, say, a puddle that's out here. And we also talked about the idea that, you know, you got air that's going to blow those guys away. So what's going to happen is these guys are going to start to evaporate. They get blown away. They're no longer available to come back into the solution. So you get less and less molecules available to drop back into the solution. And eventually what we see is our little smidge of water will eventually evaporate. And that's why what we talked about when we kind of put it into a beaker, for example, that's open, it also will eventually evaporate, but it takes a much longer time because really only the surface guys up here are able to kind of go through that process. And again, some of them will start to go away. Some of them will drop back down, but eventually what happens, right, is the volume gets smaller and smaller. Now, if we put sort of a cap there on the container and we have a liquid, this is going to allow certain guys to come out of solution, but now they have really nowhere to go, so they can kind of drop back into solution. And at some point, we will reach equilibrium where we have the rate of everybody coming out of solution will equal the rate at which they're going into solution back and forth. And it usually will end up being, maybe not this dramatic, but usually you'll end up seeing the water level or liquid level in a closed container sort of drop down a little bit because of that. And because these gas sort of molecules have nowhere to go up here, it creates what is known as the vapor pressure of a liquid. And that is basically the pressure of a gas over a liquid. So if something has a very high vapor pressure, it's said to be volatile, like we talked about, which means it essentially will go into the gas phase relatively easy. Because you have a very high vapor pressure, we know pressure is related to gas molecules. So if you have a really high vapor pressure, that means you got a lot of gas molecules being made. And if you're in an open container, you're just going to have a very high rate of everybody jumping out into sort of the atmosphere. And, you know, that's what something, when it says it is volatile, that's essentially what it means. We also saw sort of a formula about vapor pressure, which is the natural log of the vapor pressure at temperature 1 over the vapor pressure at temperature 2 equals our delta H of vaporization over R 1 over our second temperature in Kelvin, 1 over our initial temperature in Kelvin. And that was the Clausius-Clapeyron equation. That is 8.314. Remember that this delta H here is the enthalpy of vaporization, which we also talked just a little bit about. Again, we'll talk more about it in next semester, but the process of where we go from, say, solid to liquid, or liquid back to solid, it occurs at the same temperature. And there's a certain amount of heat that's required to do that. And that's what's known as the delta H of fusion, or the heat of fusion. Delta H is what is known as the enthalpy. And the heat of fusion is the energy required to do nothing more than to take a substance from the solid state to the liquid state, or from the liquid state to the solid state. And in terms of exothermic, endothermic, like we talked about, it would be positive delta H of fusion going this way, and it would be negative delta H going the other way. The number would be the same. So for example, for water, something like 6.03 kilojoules per mole. And it would be positive 603 to go from solid to liquid because you have to put energy in to melt the solid. It would be negative 6.03 to go the other way. When you remove the energy, the liquid slows down, they come together, they clump, and they become a solid. And there's also, as going from liquid to gas, and gas to liquid also again occurs at the same temp. And to do that process, that's a delta H of vaporization. And again, that energy required to do that step is the energy not to change the temperature, but to simply take it from liquid to gas. That occurs at the boiling point. This would be positive delta H of vape. This would be negative delta H of vape. This happens at the boiling point of a solution. This happens, by the way, at the freezing point or melting point of a solution. And again, for water, for example, that's 0 degrees Celsius for water. That's 100 degrees Celsius for water at the boiling point where this occurs. And again, that's what that delta H of vaporization is in there as well. Now, we also talked about, I think in this chapter as well, our sort of phase diagrams. And our phase diagrams, again, are these diagrams where we have sort of our pressure and temperature combination. And I'm going to draw it probably pretty badly, but we'll kind of go this way-ish. And we have really the different phases there. We have our solid, our liquid, and our gas. And again, you know, wherever, say, 1 atmosphere would be, that's normal pressure. And if you kind of go across, this is where we go from solid to liquid. And across this line here, this is technically where, again, melting would occur and freezing would occur going the other way. Whatever that temperature was would be the normal melting point temperature or freezing point temperature. Wherever it crossed here and you went down would be your normal boiling point temperature. And again, here, same idea. As we go this way, that is evaporation. As we head back this way, that is condensation. And coming through here, we go solid directly to gas without kind of hitting the liquid part. That is going to be your sublimation and your deposition going the other way. There's a couple of spots on here that's sort of important as well that we talked about. This part right here, I'll make the circle big to kind of connect them. That part right there is what is referred to as the triple point. And that's the point, that temperature pressure combination where all three phases are in equilibrium with each other. You have solid, liquid, and gas happening all at once at that point. Usually right where this line sort of ends is our critical point. And that's your critical temperature and pressure. And above that part is where we have our supercritical fluid occur. And as you can see, it flows really liquid into gas. There's really kind of no distinguishable characteristics. It has properties of a liquid, for example, those type of things. And it also will flow more like a gas. So it's sort of a blending that occurs in that case. And again, we use these sort of phase diagrams like we did to figure out, you know, at what sort of pressure, temperature combinations, you know, would you expect it to be solid, liquid, or gas? So you could kind of pick those things up. And I think we finished up here in this sort of chapter talking about solids and the idea of unit cells. And unit cells are sort of what happens with crystalline solids, which are very repeatable sort of patterns that occur. And again, you can take a unit cell from, say, a three-dimensional structure, pretend it's three-dimensional. And when we take a unit cell, as we talked about, what we want to do really is take a unit cell that comprises not just one whole atom, for example, but comprises parts of neighboring atoms. And that way we can really understand sort of how everything fits together. And if we pull that unit cell out, we can now know, well, if I put another one up on top, I got, you know, that deal. Perhaps I should stack another one over here. And maybe I could just fit another one here. And now you can see you can recreate really the whole entire molecule by doing so. And again, as we talked about, if you just kind of chose that, you're like, all right, I have a, you know, a circle. I'm not really sure where, you know, where the next sort of thing should go. So that's typically when we sort of choose unit cells, what we're looking for. We talked about really only cubic unit cells. And cubic unit cells, the volume is the length cubed. And that helps us find things like density, where we talked about grams per milliliter. And there's different ones. There's simple cubic, which has one atom per molecule. Basically, in the corners, there's an eighth of an atom, which gives you one whole atom. The edge length is 2 times the radius. We also had body-centered cubic. And in body-centered cubic, we have 2 atoms. And the edge length was that 4r divided by the square root of 3 in that particular case. And we had face-centered, which had 4 atoms. And the length was 2r square root of 2, basically, in that particular case. And again here, this guy, I will draw it really bad for you, again, had 1 atom on the corners of your 3-dimensional cube. Body-centered had 1 atom on the corners of that cube, 1 full atom sitting in the middle, hence body-centered. And face-centered also had an atom on the corners, and I'll just draw it like this maybe. An atom that was basically sliced in half on all the sides. And since there were 6 sides, a half atom on each of the sides, or the face of it basically, as it got sliced right in half, gave us six sides at a half atom each is 3 atoms, plus 1 in the corner gave us our 4 atoms. So this is the one where we calculate density, and most of you did pretty well on this question. You use your atoms, you use your Avogadro's number to get you to moles, and then your molar mass to get to grams, which is the grams part. Using the proper radius here, converted into meters, you could get the length, you cube it, and that will get you your volume there. And, you know, we did some calculations that involved, obviously, density and so forth. Let's see here. So that was that stuff there. We then talked about, and hopefully this stuff should be pretty familiar to you as it is getting into the last stuff that we talked about. And we talked about the idea just in terms of solutions and solubility. And let's see here. Remember the idea of like dissolves like. And that's where a lot of those intermolecular forces come into play. They need to have similar sort of ways to interact with each other. So polar things and polar things are good because they could do dipole-dipole hydrogen bonding. Ionic guys and polar, also good. They're soluble in each other for the same reason. They could do ion and dipole interaction. Non-polar guys and non-polar guys are good in each other. They're both going to use dispersion forces, which makes them work really well with each other. Really only get into a problem, as we talked about, really when we go polar and non-polar. Not so good because, again, your polar guy is going to try to use either hydrogen bonding or dipole-dipole, while your non-polar guy is going to mainly stick with your dispersion forces. So they're not going to have a way to interact with each other over the long period of time. As we talked about, in reality, everybody can do some type of dispersion forces, which is why, again, you know, like that oil and vinegar sort of dressing or water and oil, for a moment or so, they're able to sort of interact with each other. But again, to try to maintain that over a long period of time, they really don't have a way to do that. So they basically separate out from each other. So we had our saturated solution. When we talk about solids, a saturated solution is one where we've hit the maximum amount of solute that will dissolve. So if you put more solid into that solvent, no more will dissolve. Unsaturated is the opposite of that. We have not hit the maximum amount that will dissolve. So if you continue to put solid in there, it will continue to dissolve. And we also have a supersaturated solution we talked about, where you have way too much solute dissolved in the solvent. And again, it makes a very unstable type solution. So let's see. This sort of led us into the idea of talking about colligative properties. And colligative properties are properties of solutions that are based on the number of particles that are dissolved. And based on the number of particles that are dissolved in that solution, basically they will affect things like boiling point, freezing point, vapor pressure, sort of, etc. And remember that instead of the solvent being able to sort of come together to freeze in its normal fashion or escape the solution at its boiling point, with all these particles sort of dissolved in there, it creates a situation where they're unable to basically kind of do that uninhibited. And what that means is we will see things like boiling point elevation. So we'll see boiling point elevation, like where we have KB equals, not KB, I'm sorry. We have delta TB equals KB times M. This is our boiling point constant. And that is based on the solvent, as we talked about. So you want to make sure that you look up water, for example, if it's water or some other solvent and not like the solution. This is our molality, which is our moles per kilogram. And this is our change in boiling point temperature. So not the actual boiling point of the solution. That is found by taking the temperature of the solution minus the temperature of the pure solvent by itself. And again, that gives you sort of your correct addition or subtraction when you do that. And that is different than our freezing point where we had delta TF equals KF times M, this being our freezing point constant. Again, also based on the solvent. Our M again being our molality, which is our moles per kilogram. And again here, this is our freezing point. This is freezing point depression, which means this temperature, our solution will freeze at a lower temperature than normally would freeze, say, the solvent. And in that case, what we are looking at is actually the temperature of the solvent minus the temperature of the solution. And again, this is important because this will give you, instead of maybe an answer like you might put down that is 3 degrees Celsius, when it should actually be minus 3 degrees Celsius, as where the solution actually will freeze. So again, important sort of distinctions on that. We use these formulas here, as we talked about, for non-ionic solutes, so molecular solutes. When solutes are ionic, they do break apart into ions, obviously. So as we talked about, if we had something like sodium chloride, for every sodium chloride molecule or compound that goes in there, we generate 2 ions. So we're getting sort of a 2-for-1 deal, versus when we do something like sugar, which is carbon, hydrogen, and oxygen. When that goes in there, we get 1 sugar molecule, sort of a 1-to-1 relationship. So when we put the sugar in there, it's not going to have as much of an effect on things like boiling point or freezing point as when you put something like sodium chloride in there. Again, you're getting sort of a 2-for-1 situation. You got twice as much particles sort of flying in the way of these normal processes. So that's where we use that von Hoff factor, which is the I. And again, you could do it based off of the formula. So as we talked about, sodium chloride, which, as we just saw, would have an I value of 2. Calcium chloride would have like an I value of 3. And really, the place where that gets incorporated is, say, delta TF equals I KF times M. And like delta TB are the 2 most common places you sort of come across this one. And you get this. And again, that's sort of a correction value that we use for ionic solutes. And the reason we really don't even mention it when we do non-ionic is, like in the sugar example, you basically get a 1-to-1 relationship, which means essentially I here is 1. And that's how we get to the other formulas that we sort of typically use. We also talked about sort of osmosis and osmotic pressure. And basically, osmosis is the natural flow of solvent molecules from an area of lower concentration to higher. And so I think I drew probably really maybe better in this drawing here. We have sort of a membrane involved there, a semi-permeable membrane, which allows certain size molecules to go back and forth. And if we had just water on this side, and again, our salt water over here, obviously the salt water is more concentrated. It has stuff dissolved in it. Osmosis will bring the water molecules over from the left to the right in an effort to sort of dilute it. It will continue to go until it hits the osmotic pressure. And that osmotic pressure will basically be equal to atmospheric pressure that's kind of pushing back down on it. And it will stop the flow of that water molecules over there. We actually saw a formula that calculated osmotic pressure. And for the most part, it was the ideal gas law. And if you remember, this is P is equal to nRT over V. They used a fancier symbol, but really the same deal in that particular case. So you could calculate the osmotic pressure, obviously, if you have those type of things, that information given to you. Reverse osmosis, as we talked about, is when you sort of apply a pressure greater than the osmotic pressure. It kind of pushes everything back the other way. We also talked about some types of solutions which are isotonic. Isotonic has the same osmotic pressure as body fluids. And what that means is, you know, if you put, for example, everybody's classic example, which is the red blood cell, it's really just acting as a membrane, for example. In an isotonic solution, water will flow in and out of the cell at an equal rate because they have both the same osmotic pressure. So nothing bad would happen to the cell. You got hypotonic, which means less than. So again, if you put that red blood cell into a hypotonic, that means outside the cell is less concentrated than inside. So basically all the water from outside will rush in. It will cause the cell to swell and probably burst, which is hemolysis, which is probably not so great either. And we have our hypertonic solution, and that means more than. And that means on the outside here is more concentrated than inside the cell. So your poor cell there is going to let loose all its water and it's going to start to shrink, crenation, which is also not good for it. Isotonic solutions that we talked about, most people consider a 0.9% mass the volume saline solution or sodium chloride solution as sort of isotonic, and a 5% glucose as a isotonic solution. All right, let's see here. So I think we are down to kinetics, and that hopefully should be very fresh to you. We talked about kinetics a lot, and again, just to hit some of the highlights here, we have our rate of reaction, which is what kinetics deals with, and we have, if we do have a reaction such as this, we could write what is known as the rate expression, which is the rate is equal to minus 1/2 change in the concentration of A over the change in time, and that equals the change in the concentration of B over change in time, also negative, and that equals 1/3 the change in the concentration of C over the change in time. These negatives here are because they're reactants, so they should be decreasing with time. Well, we don't have the negative over here on the far side because it should be increasing with time. The 1 over the coefficient, which is where all those numbers came from, takes care of the stoichiometry or the mole to mole relationship. And that allows you to, if you pretty much know one piece of information about somebody in that reaction, you could figure out the rate at which the reactants are decreasing. You can figure out the rate at which the products are being made. Remember that the rate will be a positive number, and that's really why these negatives are here, because the reactants should start to come down in their concentration. So when you do final minus initial, which is how you do the change in the concentration, your final value is going to be less than your initial. So that's going to give you a negative. The negative there and the negative here gives you a positive value for rate. here on the back end on the product side, the final concentration should be higher than the initial concentration, which will give you a positive value for the change in concentration and a positive rate. We also then talked about the rate law, which generically looks something like this. And again, for just a reaction, 2A plus B goes to C. In this case, X and Y are not as a result of the coefficients that we see here, but they are actually the orders of a reaction and are found experimentally. So a reminder, that is where we get a table that looks something like this. And you have some multiple trials in these tables with the concentrations of everybody, the rates of everybody. And this is where we could use rate 2 over rate 1 equals K A to the X, B to the Y divided by K A to the X and B to the Y. And the goal here is, as we talked about, is to, excuse me, to try to figure out the orders of everybody by looking at the entries in that table. And what you'd want to try to choose is 2 entries in that table where one of the concentrations remains the same and the other ones basically start to vary. So for example, there we go. So for example, if, you know, entry 1 and entry 2, the concentration of A basically remains the same and B varies, you could get something like, you know, 4 equals 2 to the X, right? And the idea here is X would then equal 2 if you did that. And again, when you keep one of them constant, for example, say we kept this guy constant, they will cancel out, the K will cancel out. And again, that's how we get down here to something that looks like that. Once you do that, then you have sort of mathematically determined or experimentally determined the orders for the reaction. And once you do that, you're then pretty much free to figure out the actual constant or the rate constant, which is the lowercase k. And you could go back into this table and choose any entry and basically solve for k. So once you say get or completed rate law, say that the rate equals k a squared and b, you could go back into this and solve for k. And again, you could choose any entry you like, entry 1, entry 2, entry 3 from the table to get all these numbers. And then when you solve for it, it will give you the actual value of the rate constant. Now, we did talk about sort of specific orders of reactions, which are important. And there was basically 0 order, 1st order, 2nd order are the 3 sort of common ones. And as we talked about, really a lot of that is because there is, you know, usually 1 to 2 reactants involved. So for 1st order, there were some rate laws that we saw, which was the natural log of A equals the natural log of A naught minus KT. And also the half-life that goes with that is the natural log of 2 divided by K. And it also typically has a graph that goes with it that looks something like this. Natural log of A on the Y, T, which is time on the X, so that T is time, the K is the rate constant, A naught is the initial concentration, A is the final concentration. And again, the units of the rate constant for a 1st order is typically 1 over seconds. For a 2nd order reaction, as we talked about, we have a integrated rate law of 1 over A equals 1 over A naught plus KT. The half-life here for a 2nd order is 1 over K times A naught. The initial concentration here has an effect on the half-life. The graph that we typically associate with this one is 1 over A versus time, gives us a positive straight line. The slope of this guy is minus K. The slope of this guy is equal to K. And the units of the rate constant here is 1 over molar seconds. And we also saw a 0 order where you have the concentration of A equals the initial concentration minus kT. Half-life equals the initial concentration divided by 2K. And a typical graph is concentration versus time, giving you a straight line. Pretend that's straight, where the slope is equal to minus K here, and the units of K is molarity over seconds. So that is, again, sort of a useful way. The way you can determine what order of reaction you're talking about, if they don't tell you, is to actually just look at the units of K and determine is it first order, second order, or zero order. And you can use those equations to figure out, how the concentration changes with time. We sort of finished up talking about kinetics with the idea of temperature and the rate. And we saw really a couple of versions here, but natural log of K equals minus E of A over R, 1 over T plus the natural log of A. This is the Arrhenius equation, which basically handles time and temperature combination. If you graph the natural log of K versus 1 over the temperature in Kelvin, E of A is our activation energy, R is our gas constant, our 8.314, 1 over our temperature. A is our frequency factor, if you remember the proportional molecules that have enough energy to get up and over to the other side. We'll get that straight line where M is equal to minus E of A over R. And we can use the slope of that line to figure out the activation energy by timesing it by 8.314. We also saw a non-graphical version of this, where you could just plug and chug into this equation and obviously solve for anything. So this is sort of the non-graphical version of it. And all this really does relate to the idea of when we look at a reaction, there's this hill that everybody has to climb, which is that activation energy. And this is our reactants and our products. This is energy. And that hill that it has to climb to get to the other side is that minimum amount of energy that's required for a reaction to take place. And the greater that activation energy, the slower the reaction typically will take place because it's a bigger hill to climb. The lower the activation energy or smaller, the faster it can get to the other side. And again, by increasing the temperature, essentially what we do is we increase the proportional molecules that have enough energy to get up and over to the other side, and the reaction usually will proceed faster, and vice versa. If we lower the temperature, there's less proportional molecules that have enough energy to get to the other side, and the reaction rate will typically slow down. Other way we could do that is add a catalyst, which finds an alternative path for that reaction to take place. And when we add a catalyst, it lowers that activation energy, which by default typically will make the reaction occur faster. Whew. All right, that's the entire semester in one day. Not sure why we were here for 8 weeks. We could have just done it in one day. All right, well, I hope this was helpful for you. A couple of reminders before we sign off here for perhaps the final time. I enjoyed having everybody in the class. I hope you did as well. I wish you good luck on your final. A reminder that tomorrow I will be here for lecture. I'm not going to really do anything, but if you want to pop in or you have some type of question, I'll be happy to answer that. And again, the final will occur like at all the other exams using proctorial, and it'll occur around about lab time, about 9:30 or so. You're welcome. I enjoyed having everybody. I hope you did as well. All right, guys. Well, use the rest of your time to study. Remember, whatever you got to still turn in, make sure that you do get that stuff in, especially that take-home quiz and all that kind of stuff. So make sure you upload that. I think I need to put a spot for that. All right. Enjoy the rest of your day studying, hopefully. And I might see some of you tomorrow. If not, have a good rest of your summer. And that will be it, I think. All right. Have a good one. not sure if you're still there, but I haven't put the one up for 14. I'm going to. I remember that I need to do that, so I'll put it up there shortly.